So far we have talked only about continuous time systems. In the remaining lectures of the course, we will briefly talk about certain discrete time issues. Okay, so in other words, we're going to be talking about some basic definitions and basic results regarding discrete time systems. And in this lecture, we begin by presenting a motivation for studying discrete time systems, and then we will introduce what we mean by an including point for a discrete time system, and we're going to introduce the extensions of stability definitions that we're familiar with from continuous time to the discrete time case. Okay, so consider some plant, okay, in the real world, therefore it has some continuous time model. Suppose that that model can be linear, okay, so that gives rise to continuous time LTI system. Okay. X that equals AX plus EU. Suppose that where U is our control. But suppose that this system we want to control through piecewise constant control. Okay, so that's our goal. So what we want is control by piecewise constant input. Okay. U of t. If the input is voltage, let's say, to some step motor, during a period we want to apply some constant voltage, and then we make a measurement, we make a decision, and in the next period we apply minus 0.5 volts, in the next period we apply 1.7 volts, and so on. Okay, so what we want is, we want, for certain practical reasons, let's say we want to apply the system, we want to control that system only piecewise constant signal. So that means we're talking about an input like this. Okay, 0 U of t, t. Okay, this is t, this is 2t, 3t, 4t, and so on. Okay, so this is our piecewise constant input. So for U of t equals U, okay, K of capital T is fixed, our period for all t in kt and k plus 1 t, okay, where t is fixed, capital T. Okay, so let's see what happens to the solution, okay, under this constraint on the input. So that's the next thing that we will try to answer. What's the solution, or the form of solution for this scenario? So let's write down the solution for this continuous time LTI system, which we can explicitly, thanks to the fact that the system is LTI. Solution reads E explicit. Let's put some tildes, okay, on our matrices, because the until that versions are reserved for the discrete time model. Okay, so x of t is e to the a tilde t minus t0, then initial condition at initial time, which we denote by t0, plus this integral from t0 to future time t, e to the a tilde t minus tau, b u of tau d tau. Okay, so this is the general form of solution for any input. Okay, we don't make any assumptions right now on the piecewise constantness of the input. Now, using this general solution, we can now start studying our case where the input is fixed for a period. Okay, so that means if you want to figure out the value of the state at k plus first instant, discrete instant, we need to know two things. Well, one way to go is if you, to use the value of the state at the previous discrete time, that is the value of x at k times capital T, and then the value of input throughout the interval from k capital T to k plus 1 times T. Okay, and in that interval, we know that input is fixed, so we can take it outside the integration. If we choose the interval of integration equals to one period, okay, of length capital T. So therefore, we can write, applying this formula to our case, we can write e to the a, this by the way is the state transition matrix, okay, or the matrix exponential, a tilde. Now T is k plus 1 times T, and T0 is k times T, okay. In that case, this difference is k plus 1 T minus kt, it simply is T. So we have a tilde times capital T times the initial condition, where by initial condition we mean the value of x at k times t. Okay. X at kt plus kt to k plus 1 t e to the a tilde k plus 1 t minus tau e tilde u tau, okay, but u tau is fixed throughout this interval. Okay, so we have simply write u of kt, then u tau. Okay, all we did is we took the general solution expression and we rewrote it by setting the initial time to k times t and the final time to k plus 1 times t. Okay. And that gives us e to the a tilde capital T x kt plus e to the a tilde t, okay, 0 to t e to the minus a tilde omega b tilde d omega times u of kt, where we use the change of variables. Okay. Omega defined as tau minus the fixed k times t. Okay, and as we said, this can be taken outside integration because u of kt is fixed, it doesn't depend on tau. Then in that case, what we have is some matrix multiplying the initial condition plus some matrix multiplying the input, which is fixed throughout the interval. So let's therefore introduce new matrices. Define A without tilde as this matrix here. E to the A tilde T, and define B as this matrix which multiplies the control input. E to the A tilde capital T from 0 to T e to the minus A tilde omega B tilde D omega. Okay, so both are, so this is a square matrix, n by n, and being the order of the system, and this is D is an n by n matrix, where n is the size of the input vector. Okay, then have the discrete time linear system. Okay, x k plus 1 t equals a of x kt plus b u of kt. Okay. Now, for simplicity, let's take the sampling period, capital T, to be 1. Okay, so for simplicity, take capital T to equal 1, then what we have is x k plus 1 equals a x k plus b u k for k equals 0, 1, 2, and so on. Now this k we're calling from now on our time. Okay, it's our discrete time. And 0, without loss of generality, we'll take, because we're not going to consider time varying systems, without loss of generality, we take 0 to be our initial time. Okay. Now, although it's not as universal as the notation x that equals ax plus bu, this is a shorthand notation for discrete time. It becomes more and more widely used. Shorthand notation is x plus. Now, for continuous time system, we have x dot, now we have x plus, and x plus means the value of the state at the next time instant. Okay, so if we're at k, so x plus means xk plus 1. Okay, equals a xk plus b uk. Okay, so that's the shorthand notation. Okay, so we're imitating x that equals x plus bu in a sense. This is the shorthand notation for the discrete time system. Okay. This is discrete time LTI system, where x is in Rn, u is in Rn in general, and that tells us what the dimensions of the matrices, fixed matrices A and B should be. Okay, A is a square matrix, n by n, and B is an n by m matrix. Okay, if we have just a scalar input, in that case, B becomes just a column or a vector. Okay, now let's emphasize some basic differences, peculiarities between the continuous time system and a discrete time system, and then we're going to move on to the stability definitions. Okay, so what we've done is we've obtained from a continuous time, okay, linear system, the discrete time version, ax plus bu, where the matrices A and B are obtained by matrices A tilde, B tilde, and also the sampling period, capital T. Now let's ask the following question. How about the other direction? Okay. That is, suppose that we're given directly a discrete time system. Can we find an A tilde, B tilde, excuse me, and time, sampling period capital T, such that that triple A tilde B tilde and T yields these discrete time matrices A and B. The answer is not necessarily. Okay. So this question means, that is, can an arbitrary BT system, discrete time system, always be obtained from a continuous time system? Okay, the answer is no. And let's see why that's the case. So since the answer is no, that means in a sense that we can come up with discrete time systems through design. Okay, those systems work in our computers, let's say. For instance, the deadbeat observer, such that the behavior cannot be imitated by a continuous time system. Okay? So from that point of view, discrete time systems are worth studying, not because they're imitations of continuous time systems or approximations of continuous time systems, but they're interesting on their own right. Okay, so that's something to keep in mind. So let's put that as a remark. Discrete time linear systems can display peculiar behaviors that are not observed in continuous time, that are absent for continuous time linear systems. Okay. I'll present two examples for that. Example one is as follows. Solutions of the autonomous LTI discrete time system X plus equals AX, now we're considering U equals 0 case, may converge to the origin in finite time. Okay. That is, you start from an arbitrary initial condition and you run the system, and after finite many steps, let's say n steps, then X sits at the origin, which is our equilibrium point. Such thing cannot happen in continuous time. Okay. That is, we can have x0 different than 0 and xn, where n is some finite integer, equals 0 for some finite n. Okay. No such thing can happen for the continuous time counterpart. X equals AX. Okay. So if we have some convergence to origin, okay, it has to be exponential for the continuous time case, and even though you can converge arbitrarily fast to the origin, you will always have to wait until infinity so that you're exactly at the origin. In other words, you're never at the origin exactly, but with discrete time systems, after, let's say, 5 steps, depending on the order of the system, after 5 steps, you can be sitting at the origin. Okay. Here's another example that emphasizes or presents the difference, some qualitative difference between continuous time system and a discrete time version. First order LTI system. X dot equals AX. So let's consider the simplest possible differential equation. X dot equals AX. X is a scalar. Okay, we're talking about a first order case. Qualitatively speaking, does either of the following. Okay, well, the solution is e to the at times the initial condition x at 0. And depending on the value of a, it either blows up, okay, it goes to infinity, or either it goes toward the origin and converges to 0, or in the middle case, when a equals 0, so what we have is x that equals 0, so that means every point is an increment point, that is, you stay at where you start for all times. Okay, so that means either x of t converges to the infinity if a is positive and the initial condition is the effect of 0, or x of t converges to 0 if a is negative. Okay. Or in the order case, x of t equals constant, and that constant is the initial state x0 if a equals 0. Okay, so those are three possible qualitative behaviors. Okay. But it's obvious that a first order system, linear system, cannot oscillate. Okay, it cannot do this. But never oscillates. Okay, for oscillation you need at least a second order system. Okay, so that you have sines and cosines. And it oscillates. On the other hand, you can have a first order discrete time linear system that produces oscillations. So, however, take, for instance, x plus equals minus x. Okay. Then the solution is x of k equals minus 1 to the k times the initial condition x of 0. Okay. So if you start at, let's say, 3, then what happens is, at the next time step, you're at minus 3. And then at the next time step, you're at minus 3, which is plus 3. So you oscillate back and forth between minus 3 and plus 3. Okay? In other words, oscillations are possible even for a first order linear system, but no such thing can happen for a first order continuous time system. So there are such certain differences between a discrete time case and a continuous time case, which are good to keep in mind. That is a first order discrete time linear system can display oscillations. Okay. If, for instance, here we have minus 1 as our A matrix, if it's, let's say, minus 2, then again you will oscillate, but those oscillations will grow in magnitude. The magnitude converges to infinity, or this could be minus 1/2. Okay, the A matrix is minus 1/2. Then again you have oscillations, but those oscillations are decaying towards 0. But No such thing can happen for a first order linear system. Okay, now let's, having motivated partly discrete time systems through linear systems, let's start talking about the general case. Okay, so discrete time, nonlinear, autonomous, okay, that is time invariant, and also we're going to consider the input-free case, autonomous system. Of course, by input-free, we may mean that we have an input, okay, but then we have chosen something, a feedback law. We closed the loop with that feedback law, and then the system now can be considered as an autonomous system, okay. And that reads x plus equals f of x, or x, the value of x at k plus 1 equals the value of x at k, and then that is passed through this nonlinear mapping, okay, which we denote by f. Okay, f is from Rn to Rn. Therefore, our state x is a vector in Rn. Okay. Now, for the system, okay, for the continuous time system x equals f of x, we have said many times that we don't know. We cannot, in general, write down a solution explicitly. One nice thing about the discrete time cases, the solution is already here. Okay, so this f is our one-step solution to the future. If you want to figure out two-step solution to the future, what you have to do, you have to apply f twice, 3 steps thrice, and so on. Okay, so we can write a solution explicitly. Okay, x of k equals f applied k times of x 0. Okay, so by this notation, we're not taking the kth power because it doesn't make sense if we're talking about vectors. It's not a matrix, but this notation simply means that you take x0, this argument, and you apply this mapping f k many times. Okay, f of x0. Okay. So here we have k many f's, k times. Okay. So this is how we represent an autonomous discrete time system. Longhand notation would be x at k plus 1 equals f of x of k. Okay. So this and that, they mean the same thing, but we prefer this because it's more compact. Okay. Now, we will talk about stability now, but to be able to talk about stability, first we have to be precise about what we mean by an equilibrium point. And qualitatively speaking, equilibrium point is the same for discrete time system as it is for continuous time system. Okay? An equilibrium point is, in a sense, a solution, okay, a constant solution of the system. That is, if you start at an equilibrium point, you stay at that equilibrium point for all future times. Okay, so that's the case for continuous time system, and simply we're going to adopt the exact same definition for the discrete time case. Okay, for a discrete time system, an equilibrium point is such that if you start at that equilibrium point, you remain at that equilibrium point for all future times. So let's see what that implies on the right-hand side. For the continuous time, it implied for the right-hand side that at the equilibrium point, the right-hand side must be 0. So the derivative is 0, therefore you remain there at all times. For discrete time, it means this. Okay. Xe is an equilibrium point. autonomous system if x of k equals xe for k equals 0, 1, 2, and so on. Okay, so here we have a sequence starting from k equals 0, and then we go to 1, 2, 3, and so forth. So k is our discrete time. So that's a constant sequence. If that constant sequence is a solution of the system, okay, x plus equals f of x, or xk plus 1 equals f of x of k, then that the value of that sequence at each time, which xe, that fixed vector, is an equilibrium point for the system. Is a solution. Okay. Equivalently, if f of the equilibrium candidate equals itself. Okay. Now with continuous time, we have f of xe equals 0. With discrete time, we have f of equilibrium equals equilibrium itself. So that if you start at xe, okay, so x0 is xe. What's x at 1, k equals 1? What you do is you use the mapping to plug in xe here, and f of xc is xe itself, if xc is an equilibrium point. And then at x equals k plus 1, you're at xc. And then what's the value of state at k equals 2? You plug in x1 here, which is xc, and then since f of xc is xc, then x at xk plus at x2, again the value of the solution, the value of the state is xc, and it's clear that it will remain at that point for all future times. Okay, therefore, if this condition is satisfied, then this solution, xe, or all the solutions, xe's, they're all equilibrium points of the autonomous system. So henceforth, as we did with the continuous time case, without loss of generality, we will suppose that the equilibrium point of f is at the origin. Okay. Without loss of generality, we will let x equals 0 be an equilibrium point of the system. That is f0 equals 0. Okay? So when you write it as such, the equilibrium point condition, the condition becomes same. It looks same as the continuous time situation, but you have to keep in mind that qualitatively speaking, it's not the same. Okay, for continuous time, f of x equals 0. For discrete time, f of x equals itself, x. And you will also be considering only continuous right-hand side. F to be continuous. Okay. Now, having defined equilibrium point for an autonomous discrete time system, we're now ready to introduce the qualitative behavior from the stability point of view of such an equilibrium point. The definition is exactly the same as was in continuous time. here is the definition of stability for a discrete time autonomous system. So consider the system x plus equals f of x, discrete time autonomous system. Equilibrium x equals 0, the origin, is said to be stable if you start close enough to the equilibrium, you remain close to the equilibrium for all future times. Okay? That is, if for each epsilon positive, you can find another positive constant, delta, such that if you start in delta neighborhood of equilibrium point, the origin in this case, you remain in epsilon neighborhood of the equilibrium point for all future times, for all k equals 0, 1, 2, and so on. Okay, so that's exactly the same as continuous time definition. And if that condition is not satisfied, that is, if you can find an epsilon such that no matter how small you pick delta, this condition is never satisfied. That is, you can always find an initial condition, okay, satisfying this, and eventually the solution starting from that initial condition goes outside the epsilon law. If that is the case, then the system is the origin is unstable, if not stable. Okay. And then the stronger versions of stability, as we know, asymptotic stability and exponential stability. Okay, asymptotically stable if stable, and furthermore, delta can be chosen such that not only you remain close to the origin, but also eventually you converge to the equilibrium point, such that x delta implies in the limit you converge to the equilibrium point, to 0. And if that's true, regardless of delta, then we have global asymptotic stability of the origin. And furthermore, if this convergence is exponential, then we have exponential stability, and so on. Globally, asymptotically stable if the origin is stable and the convergence holds for all initial conditions, or all initial conditions. And finally, we have GES, okay, GES, globally, exponentially stable case if we can find a positive constant, C. In fact, it has to be at least as small as 1, but it's not very important. And a number, positive number again, that's strictly less than 1, such that all solutions satisfy this convergence behavior. Okay, the norm of the solution is always bounded by this constant, which represents in a sense the overshoot, and gamma raised to the power of k, then multiply that by the initial norm of the solution. Since gamma is strictly less than 1, this gamma to the k is also greater than 0. This gamma to the k is converging to 0 exponentially as k goes to infinity. K equals 0, 1, 2, and so on. Okay. So in our next lectures, we'll be talking about under what conditions we have these properties. First for linear systems and then for nonlinear systems.